Alright, so let us get started with gamma's function. So the first thing that arises in the mind after listening the term gamma function is that what exactly is this? Whenever we say gamma's function, what exactly is this? Look, it's a kind of operator or a function, as we have already seen that it what it does is that it generally special it's a kind of a special function that generalizes the factorial function to non-integers and even complex values function. Okay, and the main thing that is gamma function isn't defined for zero or negative integers. Okay, so yeah, I'll talk about it. So let us get started with the general definition of gamma's functions. So in general, gamma of n is defined as from 0 to infinity x to the power of n minus of 1 e to the power of minus of x dot dx, and this is the general integral for gamma's function. Okay, the main thing in this formula that is to be noted is that n is greater than 0, and yeah, I'm writing it and I'm writing this with the red, and this is a warning sign that this formula is only applicable if n is greater than 0. So let us see with different case that how we can evaluate gamma's function. So case 1, if n is greater than 0, that is n belongs to natural number. So in that case, what happens is that gamma of n is equivalent to n minus of 1 factorial. What I'm trying to tell is that gamma of 5 is equivalent to 4 factorial, which is equivalent to 24. Gamma of 6 is equivalent to 5 factorial, which is equivalent to 120, and so on. Case 2, if n is less than 0. Alright, so in case 2 also, I'll divide it into two sub portions. That is, if n is okay, that is, if n belongs to the negative real number, okay, if n belongs to the negative real number except the negative integers, and the second case and the first case is that the sub case, okay, and the second and the first sub case is when n belongs to negative integers. So as simple, for negative integers, gamma function is not defined, isn't defined. Okay, and for n belonging to negative r minus of I minus, that is for every real number except the negative integers which are undefined, I have already separated it. Okay, so for that case we will use the general formula for gamma's function. Okay, and the general formula and one of the general formula for gamma's function is again negative of gamma of n multiplied by 1 minus of n is equivalent to pi over of sine of n pi. This is one of the general formulas for evaluating gamma's function. Put the n that you want there and you will get the output there. Okay, so gamma of n is equivalent to pi over of 1 minus of pi gamma 1 minus of n sine of n pi. Okay, yeah, so this is the general formula, and yeah, and one more thing, if n is greater than 0, the thing is that if n is greater than 0 and if n does not belongs to natural number, here's one more thing, that if n does not belongs to natural number, you could even use this formula again. Okay, so that means that this formula is actually valid for n belonging to R except 0 and negative integers. Okay, so yeah, let us move on to the case number 3, that is if n is equivalent to 0 or n is equivalent to negative integers. So as simple, the function is the function isn't defined. What do I exactly mean when I say that the function is not defined? In this case, if it's not defined, that means gamma of 0 is equivalent to infinity. This will tend to infinity. Gamma of minus 1 will tend to infinity. Gamma of minus 2 is will tend to infinity. Gamma of minus 3 will tend to infinity. And as simple. Okay, so therefore, gamma's function, gamma's function is isn't defined in this case. Okay, all right. So we have seen the general integral for gamma's function, which is written as from 0 to infinity e to the power of x to the power of n minus of 1 e to the power of minus of x dot dx. The main thing that is to be seen in this integral is that this is minus x and this is x to the power of n minus of 1. Okay, and this is with respect to dx. So these are the variables, and using this analysis, and yeah, one more thing again, n is greater than 0. Using this analysis, we can evaluate several problems. Like, let us proceed further. Yeah, so like if I'll see question number one, that is to evaluate the integral from 0 to infinity e to the power of minus of x to the power of 3 with respect to dx. So if I'll compare this with n minus of 1, yeah, and this is equivalent to the gamma of n. And if I'll compare this with n minus of 1, then I'll be getting n minus of 1 is equivalent to 3, n is equivalent to 4. So the answer is basically gamma 4, which is equivalent to 6. Next, although this one is very much popular and you may have seen it before, ln of 1 over of x whole to the power of n minus of 1 with respect to dx. I'll take ln of 1 over of x as equivalent to t. That means minus of ln x as t. X is equal to e to the power of minus of t. So yeah, from infinity to 0, I'm checking the limit, cross checking the limit again and again. So t to the power of n minus of 1, e to the power of minus of t with respect to dt. So this is equivalent to 0 to infinity by using the property of integral of a to b fx dx could be written as minus of b to a fx dx. That is the limit changing property or the limit reversing property. So I'm getting t to the power of n minus of 1 e to the power of minus of t with respect to dt. And yeah, here's the normal or the general gamma's function integral that we have seen before, as I can see there. Yeah, by comparing, the answer is basically gamma n. Okay, let us look towards another problem, that is to evaluate the integral from 0 to infinity e to the power of minus of x square dot dx. Although this is halfway the proof of the Gaussian integral. Okay, okay, then also we can evaluate it. So x square, I'll take x square as t. Now the question arises that why you are taking x square as t? Because I'm getting a kind of hope. Which kind of hope? Now the hope is like, I'm saying that if I'll take x square as t and I'll proceed further from, so this will give me from 0 to infinity e to the power of minus of x square e to the power of minus of t dt half over of x, and x that could be written as t to the power of half. So this could be written as from 0 to infinity half e to the power of minus of t to the power of minus of half with respect to dt. What I'm getting here after taking x square as equivalent to t, after doing the substitution as x square is equivalent to t, is that I'm getting there e to the power of minus of t to the power of minus of half. What's the thing that is special there is that this is equivalent to the general expression of gamma's function, right? So after comparing it, I'm getting n minus of 1 as minus of half. So n could be written as half, right? So the answer to this integral is basically half gamma of half. Yeah, and the thing that is to be noted down here is that gamma of half is equivalent to pi. I'll tell it later. Okay, so this is equivalent to root pi by 2. So the answer is root of pi by 2. Next. Okay, alright, so let me introduce you with the proof of what I've told before, that is n plus of 1. Yeah, so the gamma of n plus of 1 is equivalent to gamma of n gamma n. Proof of n plus of 1 and gamma n. You could try it by pausing the video, and yeah, you could even try by pausing the video, and the hint is that it's simple. You could make an integral, that is n plus of 1 is equivalent to integral of 0 to infinity x to the power of n plus of 1 minus of 1. That's why I've written there gamma of n plus of 1 multiplied by e to the power of minus of x dot dx. And you could further use UV method and make a kind of hope in order to evaluate this. Okay, so let us move down. Yeah, so you can try it by pausing the video. Alright, so let me continue. So as I know that the gamma of n plus of 1 could be written as from 0 to infinity e to the power of minus of x to the power of n plus of 1 minus of 1 dot dx. So this could be written as from 0 to infinity x to the power of n e to the power of minus of x dot dx. Right? Okay, I'll use UV method. So this is u, this is v. So I'm getting gamma of n plus 1 as equivalent to x to the power of n minus of e to the power of minus of x from 0 to infinity plus of 0 to infinity integration n x to the power of n minus of 1 e to the power of minus of x dot dx. If in case if you have forgotten the formula, then the formula is basically uh, yeah, so the formula is basically uh, of IBP, that is integration by parts, is that integration uv dot dx is equal into u integration of v dx minus of integral of du over of dx integral of v dx with respect to dx. So this is the formula. So okay, after further evaluating the integral, I'm getting minus of x to the power of n minus yeah, multiplied by e to the power of minus of x from 0 to infinity plus of n. Oh, all right, this is the standard integral. Right, this is the standard gamma integral that is equivalent to gamma n. Right, so this is equivalent to gamma n. So I'm getting n gamma n. What about this? If I'll observe this properly, then this is equivalent to limit n tending, limit x tending to infinity minus of x to the power of n divided by e to the power of x, although this is equivalent to 0, but I'll show you the proof that how this is equivalent to 0. So limit of x tending to 0, x to the power of n over of e to the power of x. This is directly equivalent to 0. Right, now what about this? Okay, I'm evaluating here this part. Okay, so what about this? I'll apply L'Hopital rule. Why? This is tending as infinity over of infinity. So after applying L'Hopital rule or L'Hospital's rule or L'Hopital rule, anything, whatever you would like to pronounce it. So this will become limit n tending to infinity n x to the power of n over of, this is x. Okay, yeah, e to the power of x dot dx. Okay, because the integration of the derivative of e to the power x is basically e to the power x, and the derivative of x to the power n is basically n x to the power of n minus of 1. Okay, so again applying L'Hopital rule, I'm getting limit n tending to infinity n multiplied by n minus of 1 x to the power of n minus of 2 e to the power of x, and so on. I'll be getting limit of n tending to infinity n minus of 1 x to the power n minus of 2 n minus of 3, and so on up till 1. Okay, e to the power of x. So this will grow up till infinity, and this whole will go to 0. So the answer is 0. Or logically also, if you'll see it, then you will be getting that if you'll plot out the graph of e to the power of x, then it seems like in case if n is an odd function, it would be like this, right? And in case if it's a kind of an even function, then it would be like this. But in future progress, what happens is that the function e to the power x grows exponentially. That's why we called it as an exponential function. It has property to grow very much faster. You know what's special about e to the power of x? Its derivative is also e to the power of x. That means that its slope of tangent is also e to the power of x, and its integral is also e to the power of x from a to b. It's quite fascinating, right? That's the beauty of exponential function. Okay, so this is equivalent to 0. So finally, I'm getting there that gamma n plus of 1 is equivalent to n gamma n. Okay, that is concluding that this will go to 0. N plus of 1 is equivalent to n gamma n. Right. So yeah. So all right. So um, let us do some more questions like integral from 0 to infinity x to the power of n minus of 1 e to the power of x dot dx is equivalent to n gamma n. And this is the thing that you should revise more and more for n greater than 0. Okay. Uh, okay, there's one more special thing that would increase your calculation speed. And I would like to tell one more thing. I would like to admit it that you may say that how that it's a very basic thing, but in reality, if you'll focus it more and more, then this would increase your calculation speed. It's a kind of a trick or a kind of a calculation booster tip. That is, what I'm trying to tell is that this is the normal integral for gamma's function in case if I'm writing it down as x to the power of n minus of 1 e to the power of minus of, I am multiplying this with a, that is making the coefficient of x as minus a from minus 1. In that case, let us evaluate the integral and generalize the solution. This would increase your speed by 3x or 4x. I mean, you could directly even evaluate the answer using this technique. Okay, so all right. So I'll take ax as equivalent to t in order to convert it as a form of um, gamma's function. Okay, so x to the power, okay, x could be written as t over of a whole to the power of n minus of 1 e to the power of minus of t 1 by a dt. Okay, so integral from 0 to infinity 1 by a to the power of n t to the power of n minus of 1 e to the power of minus of t dot dt. And again, this is the normal or the standard. This is the standard. I'm writing it down again and again. Gamma's function. Okay, yeah, and this is the standard gamma's function, and this is equivalent to uh, gamma n by a to the power of n. Alright, so I have generalized this as gamma n by a to the power n, the coefficient of x whole to the power of n. Remember, I'm not admitting minus. Why I'm not admitting minus? I'm just comparing there. Okay. Okay, so yeah, this would increase the calculation speed more and more. And this is the generalized result. Okay, so let us practice some more questions. That is the integral from 0 to infinity x to the power of n e to the power of minus of k square x square dot dx. How to evaluate this integral? Let us see there. So again, I would like to convert it down into the general integral form. So uh, yeah, from 0 to infinity, I'm taking k squared x squared as equivalent to t. Okay, so yeah, x to the power of n, x to the power of n, e to the power of minus of t dx could be written as dt by 1 over of 2k square over of x. So this could be written as 1 by of 2k square integral from 0 to infinity x to the power of n minus of 1 e to the power of minus of t with respect to dt. Okay, now I will replace this x, so I'm getting there 1 by 2k square integral from 0 to infinity and x as I'll replace x as this will become t by k square. Yeah, so t to the power of half k square whole to the power of n minus of 1 e to the power of minus of t with respect to dt. So 1 by 2k square integral from 0 to infinity. So t to the power of n minus of 1 by 2 divided by k to the power of k to the power of this would be k only. Okay, from here as I can see that x is equivalent to t root t by k. Okay, so yeah, k e to the power of minus of t with respect to dt. So yeah, k to the power of n minus of 1. So this could be written as k to the power of n plus of 1 integral from 0 to infinity t to the power of n minus of 1 by 2 e to the power of minus of t with respect to dt. So again, this has been transformed into the normal or the gamma's function standard gamma's function. So in this case, if I am considering the standard gamma's function as t to the power of n minus of, okay, I'll consider this as m for in order to avoid confusion. Okay, dot dt. So m could be compared with plus of 1. Okay, yeah, so m minus of 1. So m could be written as n plus of 1 by 2. Okay, so this could be written as n plus of 1 by 2 gamma by 2 to the power of k 2 to the power of 2 sorry, I mean I apologize for that. So divided by 2 k to the power of n plus of 1. Okay, and here's the answer. Okay, yeah, so the final answer is gamma of n plus of 1 by 2 divided by 2 k to the power of n plus of 1. Now let us move on forward. Okay, so let us evaluate one more integral, that is the integral from 0 to infinity minus of a square x square dot dx. This is also one of the most popular question available on the internet. So a square x square is equivalent to t. I'll substitute. Wait, this question has been already done. No, this is not done. Okay, so a square x square could be written as t. So this would be from 0 to infinity e to the power of minus of t with respect to dt by 1 by of a square to a square x. Right, I am substituting a square x square as t, and you can I'm evaluating dt. So this could be written as 1 by 2a square from 0 to infinity e to the power of minus of t, and x could be, look, x could be written as t whole to the power of half a mod of a, or okay, whatever. So yeah, this could be written as e to the power of minus of t. X could be written down as t to the power of half by a dot dt. A and a got cancelled, so we are left with 1 by 2 integral from 0 to infinity e to the power of minus of t to the power of minus of half dot dt. So 1 by 2a integral from 0 to infinity t to the power of minus of half e to the power of minus of t with respect to dt. Okay, so again, this is the standard integral, and if I'll compare this with the normal integral, that is the integral from 0 to infinity, 0 to infinity, t to the power of uh, n minus of 1 e to the power of minus of t with respect to dt is equivalent to the normal gamma of n. Okay, so in that case, n minus of 1 could be written as minus of half, so n could be written as half. Right, so this could be written as 1 by of a multiplied by gamma of half, which is equivalent to root of pi by 2a. Okay, yeah, okay, all right. All right, so let us move on. So, so in the last phase, let us discuss some of the properties of gamma's function, and it's very much useful in order to evaluate different kinds of integrals and finally stepping into your final answer. Okay, so like gamma of the most important one is gamma of half is equivalent to root of pi. Okay, and as I've already told that if n belongs to integer, gamma of n plus of 1 could be written as n factorial. Okay, and 1, 2, 3. Gamma of 1 could be written as 1. Gamma of fourth is basically gamma of 0 could be written as 4. Gamma of n plus of 1 could be written as n gamma n, which I have already proved. Now, and okay, if you want to further analyze more things like that, how to evaluate. Okay, there's one more very much useful concept, that is to evaluate the integral from 0 to pi by 2 sine to the power mx dot cosine x nx dot dx. In that case, this could be written as gamma of m plus of 1 by 2 multiplied by gamma of n plus of 1 by 2 divided by 2 gamma of m plus of n plus of 2 by 2. Okay, and this is very much useful. Why it's useful? Although look, in case if Wali's formula is working in these kinds of integral. Okay. In this way only I'll tell Wali's formula. If we are discussing, so let us discuss Wali's formula. Wali's formula is very much similar to it. That is, if you want to evaluate integral from 0 to pi by 2, sine to the power mx, mnx, sine to the power mx, cos to the power nx dot dx. But there's one thing. There's one limitation, that m comma n both should be greater than 2. This is the main thing that is to be noted there, that m comma n should be greater than 2. Then in that case, this is equivalent to m minus of 1 minus of m minus of 3. Look, you can remember it like this. Starting it from limiting it to minus 1. Okay, starting with less than 1. So m minus of 1 into m minus of 3 into m minus of 5 up till 1 or whatever, to whether it's ending. And yeah, leave before 0. Leave before 0. And similarly, n minus of 1 into n minus of 3 into n minus of 5, and again leave it before 0, divided by m plus of n into m plus of n minus of 2, and so on. And again, in case if this is ending with 1, then multiply with 1 on the upper side, and in case if it's getting ended up with 2, then multiply it by pi by 2. As simple. Okay, so this is Wali's formula. Okay, so let me explore that. Is there any other property of beta's function left? Oh yeah, one more thing that striked. Okay, that is gamma n, gamma of m plus of half is equivalent to root of pi by 2 to the power of 2m minus of 1 gamma of 2m. Okay, this is also very much important, although it's not used very much vastly as this formula is used. This formula is really very much life savior. Yeah, this one. Okay, so yeah, all right. So this was all about gamma's function, and yeah, using gamma's function also, uh, we can actually derive Gaussian integral also. Gaussian integral. That's the proof for Gaussian integral. And as I've already told, the main thing is that gamma's function isn't defined for 0 and negative integers. Okay, yeah. And one more thing that is to be noted about gamma's function is that one more thing that is to be noted about gamma's function is that gamma's function is not elementary. Okay, gamma's function is not elementary. What I'm trying to tell is that it's a elementary. It's an elementary function. So it can't be expressed in form of log powers or exponents. Okay, and yeah, this thing is very much important to be noted. Okay, so basically the gamma's function is like a superpower. Yeah, you can say it like, okay, um, yeah, you can say it that the gamma function is like a kind of superpower of factorial, elegant, smooth, and far-reaching, stretching from the real number to the complex world, used from mathematics to physics and from calculus to the quantum theory. And yeah, it's used everywhere. And this is extremely important to figure out about gamma's function. Okay, so yeah, and in case of machine learning, it's used in Bayesian models. This is also very much important application in there. Okay, and in case of physics, it's always used, as we know, in quantum mechanics or in statistical mechanics, and in case of probability statistics, it's used in gamma distribution and beta distribution. Okay, yeah, so we'll be discussing about beta's function also soon. So this was all about gamma's function and the full analysis about gamma's function. So thank you.